Hey, welcome back for the last topic or the last session of the conference. So it's a great pleasure to present Marco Franciosi, who will speak on eye surfaces, Hodge structures, and canonical.
Thank you. So since I am the last speaker of the conference, I want to say thank you to the organizer for this very beautiful conference and for the wonderful atmosphere. I'm not talking only about the weather, but I'm talking also about the atmosphere among people, among the mathematicians that I appreciate very much. So thank you. So thank you, the speaker. And thank you for being here with talk. Okay. If it works.
We grew up watching video anyway.
So let me start. I'm going to talk about eye surface. And Rita yesterday talked about the general picture. Today I'm going to talk about some special features about eye surfaces. So what is a stable surface? I recall it is an S2 surface with some singularities, which in dimension 1 are double crossing essentially, and to dimension 2 are semi-local. And moreover, we ask the canonical shift to be Q-Cartier and angle. Okay, we will talk about the KX of the canonical device. Okay, what do we know? We know that there exists a compactification of the modular space of smooth surfaces, and this is called the KSBA, Collateral Barrel compactification. In our case, we are talking about eye surfaces, which mean we are talking about stable surfaces with K square equal 1, PG equal 2, Q equal 0, which means that the Euler characteristic is 3. The starting point is the analysis of the interior part of the original Gieseker modular space of such surface. And Horikawa in 1976 showed that it is unirational of dimension 28, as Rita told yesterday. And moreover, the bicanonical divisor induces a morphism, which is 2 to 1 onto the quadricone infinity, and is branched over the origin and a degree 5 hypersurface section. So we have this 2 to 1 map onto the cone. And we have the canonical ring of such surface is given by in a weighted polynomial ring, which is in degree x0 and x1 equal 1, in degree y equal 2, and degree z equal 5. So we have an equation of weighted degree 10, which is z squared plus g, which is a polynomial in x0, x1, and 1. Geometrically, this means that we have an embedding of x into the weighted projective space G11 to 5, and x is given as the locus of vanishing of our polynomial f. Since we have this 2 to 1 map into the cone, onto the cone, the remark is, as Rita said yesterday, is that the bicanonical map induces an involution x. Okay, so let me explain a little bit in the Gorenstein case what can be seen about the Hodge structure. So the starting point is the theorem which we proved with Bardini and Rolesque, which say that a stable Gorenstein eye surface, we have the bicanonical map with maps x 2 to 1 onto the cone, maybe 3, and this branch over a quintic section, non containing zero if it is Gorespian, exactly as in the smooth case. So we can study the family of such surface by studying how the branch locus varies. So studying a nice Gorespian high surface correspond to study how delta behave. And in particular, the singularities of delta give a stratification of the Gorespian loops. And the stratification, this is the picture made by Zenke. Okay, so we start with Mickey Mouse and we finish with that feather. And to be more precise, the stratification is given by considering the elliptic singularities. So we start with the mode locus, the main locus, which corresponds to canonical singularities, and then we have N1 means that we have an elliptic singularities of degree 1, and 2 means one elliptic singularities of degree 2, etc. So we have room for 3 singularities, 3 elliptic singularities, and not more, because of the geometric constraints.
So what is R?
Are 2 kind of different kind of in our case, as Rita said yesterday, R means rational and E means Enrique is about what is the singularization of the surface. In our classification, we classify the singularization and then the kind of singularities. But I don't want to enter into this. So R is rational, E is Enrique's. So, oh, okay. No. So the normal case, what does it mean? Study the singular locus of delta and then say what happens on X. Means that we have our bicanonical morphism from X onto the quadratic cone, and then I take singularities of delta and I see them like singularities of X, and then I study the exceptional curves on the resolution of the singularities. And the relevant singularities that we found and which occurs in a stable surface, if we have a quadruple point for delta, then the corresponding point on X is an elliptic singularity, and then we have the resolution on X bar, the pretty much is a smooth elliptic curve. And similarly, if we have 3 points, we have the resolution is a smooth elliptic curve of degree 1. And if the quadruple point is not ordinary, we obtain a cusp, which means that the resolution is a cycle of rational curves. In the non-normal case, we have the Collard-Fluid principle, which says that if we take the double locus and we take the normalization, we have this diagram where D bar can be seen as the conductor of the normalization and or can be seen as the double curve. And we have this mass 2-to-1 of D bar into D, and we have this gluing construction, and this gives our surface as we explained yesterday. And in our particular situation, we have this classification if we consider the case where the branch locus is non-reduced, which has a non-normal surface. So according to the degree, we obtain this normalized surface X. So we have the genus of this 0 and the genus of the bar is 1, 2, 2, 3. And if the degree of D is 4, then we have the genus D is 1 and the normalization is P2. And the bar is of the genus 2. The last line corresponds to 2 times D, which means the degree is 5. And this means that we have an reduced surface. 2 copies of the cone glued along the divisor D. Okay, so we have this rough classification. So I want to explain how to read this degeneration in terms of Hodge structures. Maybe a rough classification, but just to see. The idea is to consider simply the lean mixed Hodge structure on X. I'm not talking about limiting mixed Hodge structure. I'm just talking about the mixed Hodge structure on a fixed surface. Okay, but everything is related. So we have room since PG is equal to, but we have not so much room to obtain strange things. So this is why I surfaces are relatively easy to understand, because they provide examples, but not so complicated. So we have our Berlin mixed Hodge structure, and our point of view, as was explained to us by Collier Robles and explaining us the work about the Green, Griffiths, Lazar, Rhodes on the Hodge theoretical aspect of such surface, is the concept of mixed of structure of type Rs, of diamond Rs, which means that the number R is the dimension of H2XC in degree 0, 0, and S is the dimension of H2XC in degree 1, 0. Okay, so this is the diamond, it is rotated. And the key point is that there exists a polarized relation which says that the diamond RS is lower than or equal to the diamond TU if R is lower or equal to T and R plus S is lower or equal to T plus U. In this case, we think of the diamond TU as more degenerated than the diamond RS. And there is Hodge theoretical explanation about this. So for me, is just definition. And the key point is that if we have PG equal to, we have the following degeneration diagram, which means that we start with the diamond 0, 0, and we arrive on the right to the diamond 2, 0, which corresponds to the dimension. PG is equal to 2, so we have no room for many things to do. And the Hodge vector is 2H112. Okay, so in this case we have this kind of degeneration. And which are the slogans we use, and I'm going to explain a little bit. The starting point is that if X is smooth or if it has canonical singularities, it has a pure Hodge structure, so it is the starting point, diamond 0, 0. Then, if we have an elliptic singularity, and we consider the resolution, we have H1 is C, and this carries a Hodge structures of weight 1 if E is smooth. Otherwise, we obtain a weight 0 if the elliptic curve is degenerate as a linear progression. And if X is non-normal, we have H1 of D and H1 of the bar, which induces a mixed Hodge structure. To be more precise, looking, for instance, at the book of Peterson's tablets of mixed of structure, we have a migratory sequence. Two kinds. So the first migratory sequence we use is in the case where we consider X normal. So we have here the notation with X bar, so it is just a uniform definition. And we have the singular point, P1, Pk, and we consider the elliptic curve, which are the correspond to the resolution of the singularities. So the first exact sequence we use is this one. So we start with H1 of X bar into H1 of Y bar into the sum of H1 of the elliptic curve, and then we go into H2. So this sequence can be used to consider the H2 of X bar sequence. There is a part which comes from H2 of Y bar and part from H1 of E.
Yeah, H1 of X bar is 0 or
H1?
H1 of X bar.
It depends.
Depends.
And if the elliptic curve is singular, we have a component of weight 0, which comes from the intersection point. And so this contributes to H1. Okay? Why? If we are in the case where X is not normal and we consider the normalization, we have a similar vector sequence which comes from Migratory's theory. And this is the form. So we have H1 of X, which maps into H1 of X bar plus H1 of D, and then it maps into H1 of D bar. And this is the map relatively with the resolution. And putting all this together, we have this theorem in collaboration with Stephen Kaplan, Rita Bardini, and Zuckerlesk, which says that by degenerating our quintic section of the quadratic cone, it is possible to realize all the Hodge types in diagram terms. So this is, well, it is not a deep theorem. It is just to say that we can realize just a baby case. It is a test case, or if you want to study Hodge theoretical, the eye surface. So it is, in my opinion, that's to be considered this way. Okay. So what is the idea? The idea is simple to consider 2 points in the quadratic cone, and we consider 3 hyperplanes passing through this point, and then we consider as a divisor the sum of 5 hyperplanes, and where we take H1, H2, other planes. And then we force the configuration to obtain a quadruple point, and then we consider what happened. We have 2 points. One is P2, and then we will consider later A1. So if H2 is sufficiently general, passing to P2, we obtain an elliptic curve. So we have this situation. The migratory sequence we saw before, it is H1 of Y bar into H1 of P2, and then into H2 of X. So consider, for instance, the case N2. In this case, by our classification, Y bar is the blow up on a point over K3 surface. So we have H1 of Y bar is equal 0, and H1 of E2C maps into H2 of XC, and it is pure awake zero. In this way, we get the degeneration from diamond 00 to diamond 01. This is exactly how to build in practically such a degeneration. If moreover H2 is tangent to H3, we obtain a cusp singularity of degree 2, and writing E2 as the union of the rational curve in this way. And when considering H1 of A2 and taking the normalization of the curve, we have on each point in the intersection, we have 2 points on each rational curve, and then our Mayer-Vittori's sequence becoming this way. So we have 3 QI points, and for each of QI we have 2 points. Okay, so in conclusion, we obtain a weight zero component of the form C to the R, where R is the number of components of the curve. In this way, we get a degeneration from 0,1 to 1,0, because the weight now is in the 0,1. And repeating the argument also for the other hyperplane, we get all the strings. Starting from 0,0, we arrive to 2,0. Okay? And in the normal case, we have this situation that the section is delta 0 plus 2d. And consider, for instance, the case where the degree of d is 2. In this case, the genus of this 0, the genus of the bar, which is on the normalization, is 2. And X bar, and there is written X, no, X bar is a del pezzo of degree 1. So we get this Mayer-Vittori sequence, which is H1 of the bar into H2 of X into H2 of X bar. Then we get 0, 2, diamond 0, 2. Okay, to obtain the entire degeneration. So if one want to move from 0, 0 to 0, 2, you need to obtain 0, 1 in the middle. Simply, we consider the case where we have 2 distinct divisors, D1 and D2, and then we let D1 coincide with D2. In this way, we have in the middle an elliptic singularities, and so we obtain, etc. Okay, in this way, we can obtain all the degeneration in the diagram. Okay, I want to remark that this is a coarse classification. It's simple, an experiment. And to understand better these examples of degeneration, should be useful to consider the level 2 station data as in Greenstock, because in this way we have concrete examples and maybe can be used as a toy case for studying this kind of extension level, or maybe the things you talk about this morning may be useful. So we have this concrete example. Okay, just to correspond. Okay, so now I finished to talk about geometry and talk a little bit about algebra, and I talk about our last research about this argument. So we have our eye surface, and we want to study a canonical curve. So we let C be the zero locus of a section of the canonical device. Okay, just from the very beginning, it is, if X is not Gornstein, we don't know what is C. Is C a curve, or maybe C vanishes some component Moreover, what is the canonical sheaf of X restricted to C? And if X is 2 Gornstein, the answer is quite easy. So if we have sigma 0, a section of the canonical divisor, then first of all, C, the vanishing locus of sigma 0, is a curve. It does not vanish as a component. It is a Macaulay curve, and moreover, it is by junction, it is Gornstein of genus 2. And setting the restriction of X into C a double dual, the free part, the restriction. We have a ring of homomorphism, which comes from the canonical ring of Kx into the ring Fc L omega C, which means the sum of the power of omega C sum with the power of omega C twisted with L. Okay, so let us see what happens about the canonical curve. So in the 2 Gornstein case, if we take C to be a canonical curve, then we have 2 cases. We have case A, which is C is irreducible of genus 2, or C is given by 2 rational curves meeting in 3 points. And the other case is that C is given by 2 elliptic curves meeting in 1 point. So case A is explained in this drawing, in case B. So we have 2 elliptic curves. I draw a curve just to say that it is elliptic. Maybe smooth or rational. Okay. Moreover, in case A, C is hyperelliptic in the sense that the canonical divisor induces morphism to 1 to Q1. In case B, the canonical system has a base point. And considering the bicanonical map of C, we have this geometric interpretation. In case A, we obtain a morphism onto a conic. In case B, we obtain a morphism onto a degenerate conic, onto 2 lines. And this characterization allows us to compute the half canonical ring of C, which is the one I explained before, in these 2 different setups. And we obtain this conclusion, which says that taking the computation of the half canonical ring, considering the generalized Kodara events, and considering the Maastricht-Zucker-Klein section principle, which says that one considering the restriction, the curve, we can build the generators and the relation on the surface, adding 1 generator. So we obtain this theorem. If X is an I-surface, and assume X is 2 Gornstein and C reduced, then if C is of type A, the canonical ring is exactly as in the smooth case. If C is of type B, the canonical ring is a little bit complicated. We have generators in degree 1, 1, 2, 3, 4, 5, 6. Relation in this way. So we have the vanishing of the 2 times 2 minus this matrix, and these other relations, which are a little bit complicated at this side. And the geometric interpretation of of those canonical rings. In case A is the following. X is embedded in P1125 of degree 10, exactly as in the smooth case, and X is mutable. And in case B, X is a reducible surface, is given by the union of an Enrico surface and a Cater surface along an elliptic curve. And even in this case, the surface is mutable as well. It's mutable in a different way, not so obvious way, but it is mutable. The equation coming from the vanishing of the 2 times 2 minus give the two weighted subspace where the two components lives. So I don't want to enter into the details and the subordinate, so I can stop here.